So lecture 2 we were studying about alkanes. Anything from there? Nomenclature we did first, and later we were talking about a very complex topic for cycloalkane. Remember? And then we did that boat and chair conformation. I always have questions from this topic, so I am expecting this year would not be any different. How do you feel about the chair form and boat form? Are there any questions? Everything is clear, is it? So two things we need to remember about the chair and boat form. Boat form not so much, but yeah, chair form mainly is that there are two types of bond in chair, equatorial and axial. How do we tell which one is what? So if the bonds of hydrogen are parallel to the equator of that chair, then they are called equatorial bonds. And if they are parallel to the axis of the chair, then they are called axial bonds. Remember? And then which one was more stable? For example, if we put any one group on cyclohexane, where that group will be placed? We did discuss that, right? That for axial bond, they will have the flag pole interaction, and because of that, the molecule will have some hindrance. Therefore, any group which will be attached on benzene ring, not the benzene ring, cyclohexane ring, would want to be on the equatorial position. Right? So if the group which is present on the cyclohexane is on axial position, how can we convert that into equatorial? That was the question for which we saw an animation last week. Remember that if the chair is having its back on right hand side, then you can flip it over, which goes through the board conformation to the other side of the chair. And in doing this flip, we call it flip, or interchanging the chair into one from the other form, will convert all the axial bond into equatorial bond. Or otherwise, if the bonds were already in axial form, they will be coming in equatorial form. Or if they were in equatorial form, they will be coming in axial form. So this flip you should understand. That was the whole point of showing that animation. Why this is important, equatorial and axial and all these new fancy names? Because one of them is always outside the plane and the other one is inside the plane. So in some cases we may need one of the isomer as opposed to the other isomer, so we should be able to control the stereochemistry of the incoming group on the cycloalkene ring. Because that makes all the difference in the stereoisomers for the cycloalkene, isn't it? If it cis in one form, meaning that both of them are outside the plane, then it would also be cis in the other form, where both of them are inside the plane. But when both of them are on opposite planes, then we may need to control their stereochemistry, that which one we want outside the plane and which one we want inside the plane, right? I think it's working fine now. I restarted the video. But can you hold for like 1 minute maybe? I can check one more thing. Thank you so much. that's where we were last week, right? Here. So what I am emphasizing again and again is there you see how we have changed this axial group, which is methyl right here, by flipping into both first and then the other chair, and then by doing so this axial bond is now into equatorial position. And this equatorial always will have higher stability because of the absence of that flagpole, which comes right here if the group is already on axial position. Right? Here is one hydrogen. Now this hydrogen interacts with this methyl, that's why this is not so stable. So this group needs to be always on equatorial position. So when there are two groups, then always the heavier group, meaning the one which is bigger in size, should be placed at equatorial position, and the other one we don't care. Because of course we can only control one of them. If one of them is axial and another is equatorial, you will flip, the other one will become axial and the first one will become equatorial. So out of those two groups, the one with the heavier size, meaning bigger size, more number of atoms, should always be placed on equatorial bond, right? So no questions, is it? Everyone is happy from the previous lecture? Unfortunately, we have lost so much time, so I will not go into the regular review of things, but I owe you this one, probably in the next one. Right, so the final topic for this chapter is to learn about the chemical properties of alkanes. And when we say chemical properties, it means two things: what type of reaction they do, and from what type of reaction they can be obtained or synthesized. So there are basically two types of reaction by which you can synthesize alkanes. First type of reaction is called addition reaction. So addition reaction, as the name suggests, it will have some small molecule adding up into another molecule to make up an adduct, right? Like 2 plus 2 will become 4. So here, one molecule plus another small molecule will become one new molecule. These type of reactions are called addition reaction. Why? Because one small molecule is being added into the other reagent, right? This is the first reactant, and then this hydrogen is being added into the new molecule. By doing this reaction, what are we getting is that the carbon-carbon double bond is being converted into carbon-carbon single bond. So meaning if you have double bond or triple bond anywhere, you can add a small molecule in that molecule, right? If you will keep this in mind, this will be very helpful in many other chapters as well. So these type of reactions are called addition reaction. But the point of showing here as an example is that this is one way by which alkanes can be synthesized. So you can start with alkenes or alkynes and then add hydrogen molecules in them, so your double bond or triple bond be converted into single bonds, and that's how you can get alkanes. It doesn't matter if you have alkyne, then you will probably have to do two sets of addition reaction. First, alkyne will be converted into alkenes because triple bond will go into double bond when you only add one molecule of hydrogen. But if you add another molecule of hydrogen, then you will have two sets of hydrogen molecule added into your alkyne, and hence you will get carbon-carbon single bond. This makes total sense, right? So this is one way of synthesizing alkanes by utilizing addition reaction. For that you can use alkenes as well as alkynes. These are some specific examples which are taken from literature, so don't get confused by this fancy structure. This is just an example taken from literature. Literature meaning the actual example by which people synthesize this compound from that compound. Now this compound would be of interest to somebody, that's why we have taken an example here. But for us, its structure is not important. Well, we could simply see that even in the presence of other groups, this reaction works quite well. And then triple bond gets converted into single bond. As simple as that, right? The other things, they really don't matter if you are using proper system of catalysts, right? So for this purpose, you can use platinum, palladium, or nickel. It really doesn't matter because we want to take multiple bonds to single bond level. If we want to start this reaction at a certain point, then we might need to take some selective catalyst into account. For this purpose, no problem. Any metal would do as long as you are putting hydrogen in that. That will always be added on the carbon-carbon multiple bond, and those will go all the way to carbon-carbon single bond, right? The other example by which alkanes can be formed are the opposite of what we have just seen. So that reaction was addition reaction. These type of reactions are called elimination reaction. Yes. I cannot hear you. I is going to announce on the group, then we will do physical class together. Is someone asking you for me to on it? Where are they? Okay, I will do it. But since I announced today that we will have physical class, that's why I didn't do the BB collaboration. Hello, online students. Hello, online students. You haven't missed anything yet, but I was expecting everyone in the physical class today, hence the delay. Never mind, now we are here. This is being recorded, so you can always get back to it, right? So, the other type of it, please. The other type of reaction by which we can get alkanes are called elimination reaction, which is just the opposite of addition reaction. So in addition reaction, you add something in another molecule. In elimination reaction, you subtract something from the main molecule. So here are loads of examples of what type of molecule you can start with. And if you take out something from those molecules, you'll end up getting alkane as a product. So those examples are alcohols, aldehyde, ketone, carboxylic acid, and multiple derivatives of carboxylic acid. So you can start with any of these, and if you do this reaction in the presence of red phosphorus and hydrogen oxide, which are very strong reducing agent. Reducing agent are the one which can either take out the hydrogen molecule from something, or they can take out the electrons from something, are called reducing agent. So in this case, they are taking away the hydrogen molecule from the parent starting material, and by taking out that hydrogen, we will get alkanes. How does it look like in actual world? It is just like that. So this is OH of alcohol, and then this is your neighboring hydrogen. So all together, if you take out something like that or something like that, you will get your carbon-carbon single bond, and this thing will be eliminated from it. Not this, yeah, everything needs to stay in here. So by eliminating this small part from the molecule, you will get the required alkane. So this is one example. Alcohol will do, or any of these functional groups will do. The main reaction is elimination because one part is going off from the molecule. In this case, water is going off. Water, water, water. In this case, two alkanes are being formed because many things are getting off from here. In this case, some other things are getting off. But things are being eliminated from your starting material. That's why the name elimination reaction. And as a result, we are getting our regular alkane. So you can decide based on your resources and your expertise in the lab that how you actually want to synthesize alkanes, by elimination reaction or by addition reaction. As far as your course and exams are concerned, so any example from both of these two cases would suffice. You don't actually need to memorize from every single example because these examples are not from all over the world. These are some examples, selected. There are more examples as well by which you can synthesize alkanes. So as long as you know the principle that doing these kind of reactions we can get alkanes, you're good to go. I get these questions in our WhatsApp group that do we need to memorize. So as little as one example would do. That's what I want to do. Yeah? Right. These were the examples from which we can synthesize alkanes. Now how about what types of reactions alkane do? So combustion reactions are burning of molecules in the presence of oxygen, and this reaction is common for all organic compounds. All carbon containing compounds which are organic compounds would do combustion reaction. Alkanes are no different. What happens is that you can take any alkane and then heat the reaction in the presence of oxygen. So you will always get the same product, carbon dioxide and water. And of course, some amount of energy will be released because this is a combustion reaction, right? So if you don't remember ever any chemical properties of any functional group, combustion reaction would be your friend and you can just put it there. Here we have example of alkane. If you're talking about alkene, same reaction will happen. If you're talking about alcohols, this reaction stands for all organic compounds. And alkanes combustion is really important because we use this as gasoline in cars, in our gas cylinders at home, all those things. We use combustion of any simple alkane which will give us the form of energy. And always the byproduct will be carbon dioxide and water, right? Beside this, so two types of reactions and two types of synthesis we have seen today. One synthesis was addition, other synthesis was elimination. In terms of reactions, we are seeing again two types. First type was combustion, and second type is basically called substitution reaction. So these are, as the name suggests, all these reactions, addition, elimination, substitution, they simply mean what they look like from their name. So substitution would mean that something will get substituted, meaning replaced with something else, right? So what happens here in the case of alkane is that if you react a simple alkane, for example, methane, with halogens such as chlorine, this reaction can be done in the presence of sunlight or in the presence of actual heat in terms of flame or something by heating. So one chlorine atom will substitute one hydrogen of your alkanes. And as a product, you will get alkyl halides. Remember that this type of functional group, we looked at them in our last week lecture, are actually called alkyl halides because alkyl part and halogen part. So why not alkyl halides? That's their name. Other examples are there that this reaction will probably not stop there. It can continue to go all the way until all hydrogens are actually substituted from your parent alkane. If you want to control this reaction to any of these stages, you have to do additional measures because these type of reactions are quite reactive. So generally we get all substitution which are available here in terms of hydrogen. So what are we seeing here? That every time one hydrogen is being replaced with chlorine. Hence the name substitution reaction. Here one hydrogen is gone, one chlorine came. Another hydrogen gone, two chlorine, and then so on and so forth. So these type of reaction, they occur by something we like to call as free radical mechanism. Now this is the first example of mechanism we are looking in this course. I think the other examples would come today. So any reaction what we see in the equations does not go like that. The equation is written as a shorthand to tell that what is happening. There are multiple steps going on in every way of the reaction, and that steps are being explained by something we call as mechanism of the reaction. So mechanisms are of different types. There are at least like tens of types of different mechanisms. Free radical mechanism are not that common, but not that rare as well. I mean, you could get free radical mechanism in a lot of different types of reactions, and this is just one example of that. The substitution reaction of alkane by halogen occurs with free radical mechanism. How do we know this information? Is it something that just is written in textbook, or how can we actually tell? So all these steps which we see in the mechanism are proven in laboratories to finalize that this is how the reaction is progressing to give this product from that reaction. So these are not theoretical things. How we are drawing them here may look like that, well, this is all in the thin air, and probably we will not be able to check it that if it's really happening like that. But that's what I'm trying to tell here, that the mechanisms are derived experimentally, right? Now what happens in a free radical mechanism? In simple words, it consists of three steps. Step 1 is called initiation, step 2 is called propagation, and step 3 is called termination. By the way, is there anyone, because no one asked me, so how would I know? What is a free radical? What is it? Is it an element? Right, so what is a free radical? Ions. So ions are everywhere, right? Are they ions actually? Because ions are ions. Why are they called free radicals then? And why not ions? Anyone else would like to take a dig?
A group of atoms that has charge.
Where is the charge? Do you see negative, positive charge on that?
The electron.
So it does not have a charge yet. Even though it has a okay, so this student say that free radical is something which has excess electron. That's what you say. Am I quoting you correct or not? But it does not have a charge, that's why it's not an ion. So whatever reaction happens, you will have many intermediates. That's what I was telling you. That equation of the reaction does not do justice to what is actually happening. That reaction occurs with a series of many steps. And during those steps, some things are formed. Those things are called intermediates. So intermediates are of different types. Some of the intermediates are ions. They can carry positive or negative charges. Some of the intermediates are free radicals. Free radicals are simply elements or group of elements which carry an unpaired electron. An unpaired electron, that's the key word. Not a lone pair of electron, as you would see in ions. Or the deficiency of the whole pair of electron, as you will see in positive ions. Here we are talking about single electrons. So that's why they don't have the whole charge. Positive charge would mean deficiency of a pair of electrons. And negative charge would mean increment of a pair of electrons. But free radical would only mean excess or deficiency of single electron. So this is the type of intermediate which are involved in this mechanism. That's why the name is free radical mechanism. Does it make any sense? So what do I mean by this is that the intermediates of different reactions would be different from each other, and based on that the mechanism would be different. So you can expect that how many different types of mechanism could be there. Probably tens of different mechanisms are there. For our course we will only focus on a few, and this is the first example. So this is called free radical mechanism because the intermediate of this mechanism is based on the formation of free radicals, hence the name free radical mechanism. What happens is that instead of getting the whole pair of electrons, each atom only takes one electron each, and that's why free radical. Now these free radicals are indeed super reactive, so they react with whoever they want to react with. In this case it's methane. So with the movement of electrons from the hydrogen to the carbon and from the free radical extra electron, they make a new bond of HCl like that, and as a movement of this electron from this part, we get a new free radical, which is methyl free radical. So free radicals, whoever they meet with, they would like to make another free radical because they don't have a pair to give or take, so they could only share single electron from the other thing which they are reacting. So on that basis we do get this methyl free radical instead of regular methyl ion. Why? Because we started with the free radical in this reaction. And this is the virtue of this reaction. How do we know that this goes with free radical and not the ionic mechanism? That is an experimental fact. So how would you know? This is some memory that you have to keep in mind, that what reaction goes through which mechanism. We don't have many examples in this course. Ideally we only have 3 or 4 examples, and this is one of them. So you have to remember this, that the substitution of alkane proceeds with free radical mechanism. This is the information you will need to remember. Okay, I'm so sorry, I know it sucks to memorize so many things, but you cannot do this experiment, right? If you could do, then it's easy to tell. There's a machine called EPR. You put your reactants in that, and then it will identify that if it is forming ions or free radicals. That's all. Anyway, so once you have this new radical formation, the process could go on until you are satisfied with your product, and you will get a new free radical in every step. That's why the step is called propagation, because many free radicals are being formed. And finally, once you are satisfied that yeah, this is your product, at that time you can think of terminating or ending the reaction, hence the name termination step, where these free radicals will give back the electrons to each other and will become the whole molecule again. So these are the 3 simple steps of free radical mechanism. It does not matter which alkane you take, this reaction could continue until all available hydrogens are replaced with the halogen in this case. Alright? So what was the other reaction we looked at for alkane besides the substitution reaction? Combustion. Awesome. Perfect. Unfortunately, alkanes, they don't react with acids and bases and common reducing and oxidizing agents. So that's a good thing for you. You won't have to memorize more reactions. So alkanes are quite benign in terms of their reactions. They only do limited types of reactions, which we saw. The other common reactions, such as reaction with acid or base or reducing or oxidizing agent, no. Alright? So with that, we are done with the chapter of alkane. I will be happy to take questions for 5 minutes now. And I apologize for so many delays today. You learn, and then these things. Right, do we have questions from the previous chapter? Now I have. Any other questions? I mean, any question. That was not a question. No? Is it that you are not interested in chemistry, or like it's the time, or is it me, or like the combination of everything? I mean, I have a lot of questions. I am teaching, but still I have like so many questions right now. For example, the one I asked you about, that how do we know that which reactions work? Or is it that just you have to memorize everything and then you'll pass your exam? Question a lot, otherwise all the subjects will become boring. If you get to know the answers, perfect. Maybe you ask the question which nobody has answered before, but that will be the topic of your research in future. Why not? Yes? Right, so we will take 4 minutes of break now if you need water or anything. In the meantime, I'll upload the slides as asked by Sri.
我去打呀，他优先，他不能有。我还森林，我没有他有，我去打盾了，打了盾，there's no way. I feel like really small damage.
Rahman, Anson, anyone here? Anson, okay. Arun Raj. John. Okay. Deborah. Deborah. Alright then. Oh, we have a question.
Sophie is a bigger face.
Where did that student go?
Yeah, I think it's bigger face than him.
Ah, yes.
Yeah, he looks like him but younger.
Have you written down your question? Alkenes. Carbon-carbon single bond has less bond strength than carbon-carbon double bond, and so on and so forth. More is merrier in terms of strength. But this is when we want to get the alkane from something. If you ask that, well, naturally, if there are more alkanes or alkenes, I wouldn't know the answer. That will tell that which one of them are actually more stable. Does it answer your question? Right, so now starting with our chapter 3. Right, so chapter 3 is about alkenes and alkynes. Okay, meaning carbon-carbon double bond and carbon-carbon triple bond. Why I have put them together in one chapter is because of their characteristics are quite similar. The types of reaction they do are quite similar, and they are combined in one chapter. We will see that how much we can do today. I don't think so that we'll be able to do both, but yeah, it doesn't matter. So the learning objective for this chapter are these 4 or 5 things. Of course, always for every class of compounds, we want to know that what is their structure, because that dictates their properties a lot. We will briefly look at nomenclature for each of these classes, because the main rules are same. The rules which we studied for alkanes will apply on alkenes as well as on alkynes. Then again, their chemical properties and some mechanisms at the end we will look at. Right, so alkenes are actually hydrocarbon compounds, again, like alkanes, because they are only made up of carbon and hydrogen. But the difference or their functionality, how it differs from alkane is the presence of carbon-carbon double bond. So if you see carbon-carbon double bond anywhere, you could easily tell that this molecule belongs to alkene class, which we will do in our tutorial 1. Some of you might have done it today, but some of you will do later this week. So alkenes are also called olefins from the fact that they are oil-forming gases. So in some other language, their common name was olefin, which is also used till date in normal sectors. Industry, a lot of industrial applications these molecules have, including alkanes, like we discussed in previous chapter, gasoline and all those things, and then the household gas, which is used for cooking and all these things. So similarly, alkenes and alkynes also have widespread industrial and household applications, which we'll look at later. Right, so here are a few examples of very interesting alkene molecules. For example, vitamin A, it has so many carbon-carbon double bonds, right? So important for eyesight and these kinds of things. Cholesterol, very important hormone, very important steroid. So that has a carbon-carbon double bond in there. You could classify them within alkenes as well. Rubber, for example, and then all the plastic that you know of, mainly like 80-90% is actually coming from the alkenes class. So rubber as a natural polymer has so many carbon-carbon double bonds. So these are just to name a few examples of important alkenes which are found in nature, right? Oh, okay. Right, so the structure of alkene, how it differs from alkane, is the presence of carbon-carbon double bond, right? So you remember the valence bond theory for this structure explanation of alkane? The only difference in alkene is that there we had like 3 hydrogens available for each carbon. Here we only have 2. So this means that only 2 orbitals can be utilized in making single bond with hydrogen. What will happen to the unutilized remaining orbital in case of alkene? So that unutilized remaining p orbital of each carbon with the sidewise overlapping makes a new type of bond which is called pi bond, while the normal carbon-carbon single bond or carbon-hydrogen single bond are actually called sigma bond. So these new type of sidewise overlapping give rise to the formation of this pi bond. So carbon-carbon double bond is actually one sigma bond and one pi bond. Does it make sense? Now the actual representation of these orbitals or the groups which are attached on each carbon needs to be away from each other as much as possible, as we looked at in the case of alkane. So in that case, the bond angle was about 110, right? And the structure was tetrahedral. While in this case, the bond angle is 120 and the structure is trigonal or planar. In some books you will find it. Why we call it planar trigonal? Because it can be present on this plane itself, the carbon-carbon double bond. And then one of them will be outside the plane and the other one could be still on the same plane. So you see the difference between the tetrahedron and trigon, right? The tetrahedron, one of them will be away and one of them will be towards you. While in this case, 2 of them will be on the same plane, only one will be either away or towards you, if you put it into the 3D perspective. So that's why these are planar trigonal molecules. Right? A lot of confusing face I see. It smells like that you have a question here. No? Now those confused faces are giving me a fake nodding so that I don't ask you the question. Right? Okay, so do you able to see in terms the actual 3D world that we live in, how the structure of alkene is different from alkane. No? Right, that's what I was thinking about. That your nodding was not that convincing. So I found that there was some confusion. Right, so for a molecule to be considered, you have to put it into real world application sometimes to see it more clearly. Now if you're talking about alkane, so imagine that if the middle carbon is at this corner, so you will have this carbon and then this one on the same plane. Then one would be away from you and one would be towards you. That would be the actual structure of alkane because it's a tetrahedral. While in case of alkene, it's only planar. So two of them would be here, one is there and one is there. Now the third one will be either away from you or towards you, not both. So that's the main difference. So if you consider that this is the other carbon, then yeah, two of them on this plane and the other one is away from you. That's perfectly, well, normally in 3D world it will work like that, right? So you need to put these kind of images in your mind, otherwise these petals, they don't mean anything. These are just the way to explain them in theory. What they actually come to is their real structure, which you need to put in your mind for the rest of your life. Or at least until you give the exam. Right? So you now see the difference between the two? The other explanation is there. I think it's just boring. The only difference is that we don't have enough hydrogen here to make all the sigma bonds. Right? So the leftover orbitals will do a new thing which is called sidewise overlapping instead of head-on, which made the sigma bonds in previous cases. So here we have sidewise overlapping, which gives rise to a new bond, which is pi bond, and that is the carbon-carbon double bond we are talking about. Right? Alright, physical properties. Generally speaking, everything is same, but they are slightly more polar than the alkenes, and hence they will have more kind of reactions. Why they are polar? Because this new bond is actually additional electrons, right? So in alkanes we only had one bond, meaning the two carbons were joined by two electrons. Now we have carbon-carbon double bond, so these two carbons are joined by 4 electrons. So these extra electrons will give molecules some polarity and hence some increased reactivity. Right? While all other things, they stand for every organic compound, isn't it? Most of the organic compounds, if they don't carry any halogen, they will be less dense than water. And then branch alkanes, these 2 points are same as alkene, right? Like normal will have higher packing because of symmetry, while branch molecules will not be packed properly and hence they will have lower melting and boiling point, right? Okay, let's quickly glance through the IUPAC nomenclature. The rules remain same. Probably I can skip to the actual examples for you to note down. The only thing you need to remember is that the longest chain which you used to select for alkane, now it should include the carbon-carbon double bond within that longest chain. If you choose a longer chain which does not have the carbon-carbon double bond as part of it, then that would be not right. So your longest chain which you will select in the given molecule, the carbon-carbon double bond should be part of that longest chain. Right? And then there we used ane, so here we use ene of course because these are alkenes, right? All the other things remain same, so here you have it. You have to give the numbering of the position where the double bond is starting, right? So one could argue that why don't we write it as 2-butane and why we are writing it as 1-butane. So from the sequence you can tell that double bond is starting from 1 to 2. So that's why we have to write the position from where the double bond starts. So this would be 1-butene, 1-pentene, 2-pentene, 2-butene. No problem whatsoever here, right? And if the compound is cyclic, then you don't need to give the position because ring is symmetrical, right? So if this bond is here, it does not make any difference. If it was there, it will still be called cyclohexane. Yes.
Can I use the format in text one in
You can, definitely, no problem. So in some text you will find pen to E. That's also fine. Right? So ring nomenclature continues. Once in the cyclic structure you also have a branch there, then it gets interesting. Now you have to give numbers. Why? Because now we don't know where exactly on the ring the double bond is relative to the branch. Right? If you move this double bond there, then we could say that the branch is 2 steps away from the double bond. Right now it's only 1 step away from the double bond, right? If there are 2 things in the ring, including the double bond and a branch, then numbering becomes relative and therefore you need to give numbering. But if it's only 1 branch or only 1 double bond, like in previous cases, you don't need to worry about numbering at all. Right? Here this numbering is irrelevant. But when we have 2 things, then the numbering becomes important. So here it's like the branch is present on the carbon-carbon double bond itself. Here it's 1 step away. If you move the double bond there, then it will be 2 steps away. So therefore, the numbering becomes important. Now, branch is just branch. You will start the numbering from carbon-carbon double bond, and that's how you can tell that what is the name of this molecule, right? Similarly, you will start from where the double bond is starting. So you have it like that. 3-methyl cyclopentane. Why you didn't start it from there to there? Because it will not include the double bond. If you start from here to there, then it will be long way around. So it needs to be closer to the numbering, right? The branch should get the least number. Remember, that is the basic principle of IUPAC. So for that reason, we have to do numbering like that. Does it make sense? Why we can't do numbering from there to there? Because then the branch will be too far away. Right, so the trivial stuff is gone. Now let's talk about the stereoisomers of alkene. They are super important and they are what give them some importance about their structure. So technically you can have 2 sorts of nomenclature to explain the isomerism in alkenes. One is called cis-trans isomers, another is called E and Z isomers. So let's look at cis-trans first. So I am sure that if you have taken basic organic chemistry before, you are familiar with that, but if not, then you are also my friend. So how can we tell the 2 different types of isomers from each other? Is to look at the carbon-carbon double bond in this direction. You have to look at if the heavier groups are at the same side vertically or they are on the opposite side. So if they are on the same side, then you can call that isomer cis, and if they are on the opposite side, then you can call the isomer trans. So we have to look at it vertically. Right? So here, these 2 are on the same side of the double bond, right? Same side. You look at my hand movement, so vertical. And then here, they are on the opposite side. These 2 are the heavier groups, right? Now I am doing horizontal movement, but how we are looking at them? Vertically. That's why it's important to keep this in mind. This will be the differentiation between E and Z and cis and trans. So anyway. For cis and trans, we have to look at it this way. If the heavier groups, meaning the one in bigger size, are on the same side of the carbon-carbon double bond, then they are called cis. All the other rules still remain same. So it's called cis 2-pentene. Why? Because 1, 2, 3, 4, 5, so pentene. And then at 2 position we have the double bond, right? So 2-pentene might as well be the other, isomer. Right? Is there any question here? Especially from those who have not heard it before, cis and trans. So how you will decide that? You will look at them vertically, that those groups are on same side, or they could be same side downwards as well, or opposite side. Right? That's what we are looking here, right? That these two are the bigger groups and they are on the same side. These two are the bigger groups and they are on the opposite side. Correct? Right. So cis and trans fails terribly in many instances. It will work best when you have similar groups on the carbon-carbon double bond. But when you have other important functional groups, in some cases, they would be part of higher priority in giving numbering. So ideally, E and Z nomenclature is more of a new thing than cis-trans. Cis-trans is kind of obsolete these days. E and Z nomenclature gives us clear rules and regulations to differentiate between different isomers of alkene. But to do that, you might not have studied this before, so I will take some time here, don't worry. So E and Z nomenclature comes from a newer convention. Like IUPAC is a body, you know the full form, right? International Union for Pure and Applied Chemistry. That's a governing body which decides on these rules. So within this body there are different conventions, like a constitution will have different conventions and different alterations and moderations all the time. So one of those convention is called CIP convention, and that comes from the name of these three scientists, Kahn, Ingold and Preload. One of them is not German, but the two of them are German. Now which one is not German, I always forget. But it's not important, right? Majority of them are German anyway. So CIP convention tells us to systematically tell the different isomers of alkenes apart from each other. To do that, what you need to do is you have to assign priorities to every group which is directly attached to the carbon-carbon double bond. And this priority will be given on the basis of higher atomic number. Right? So you will look at each of the thing which is attached to carbon-carbon double bond, and you will decide on their basis of higher atomic number. If any group has higher atomic number as a whole, then you will say that this one has higher priority, and the other group will be lower priority. And if the high priority groups, after doing all the assignment of priority based on atomic number, if the higher priority groups are on the same side, then they are called Zusammen. This is a German word for together, I guess. I may be wrong, I am not expert in German, but yeah, as the textbook says. But we indicate that with Z, as for Zusammen. So Z would mean that high priority groups are on the same side. And then E would mean that they are on the opposite side, and E comes from the German word Entgegen, which would probably mean opposite side. Right? So how about we look at the examples and we will know more, right? Otherwise it's all word in there. So let's look at one example and it will make total sense. While for cis and trans we were looking at things vertically, in this case we look at things horizontally. Right, we'll cut the carbon-carbon double bond in the middle. This is one carbon. So what is attached to it? One carbon and one hydrogen. We generally don't look at things as a group in CIP convention. We look at the next connecting atom only. We will see another example soon. So here the next connecting atom is carbon, and here the next connecting atom is hydrogen. So hydrogen has atomic number 1, carbon has atomic number 6. So based on atomic number, this takes high priority, right? So this is number 1 and this is number 2. Now we forget about this part. We go to the other part. Here we have bromine, the next connecting atom. Here we have chlorine, the next connecting atom. So out of these two, bromine has higher atomic number and chlorine has lower atomic number. So this takes priority 1 and this takes priority 2. Now the two higher taking priorities groups are on the opposite side. So that's why this isomer would be E. If they were on the same side, meaning that this one was also there, meaning if you take bromine there and chlorine here, then it will become the Z isomer. But for now, as it stands, since the two high priority groups are on the opposite side, this would be E, 1 bromo, 1 chloropropene. I mean, rest of the rules, they remain the same. But we have to put this E or Z to the nomenclature to tell clearly which isomer are we talking about. Yes?
How do you determine high and low priority?
Based on their atomic number. Right? That's what I try to say. That we have to look at the next connecting atom and we will know the atomic number of that, atom, and then we can tell that which one has a higher atomic number and which one has lower atomic number. And higher atomic number will have higher priority, lower atomic number will have lower priority.
Is it just the atom or the whole molecule? Like, do we count just carbon or carbon and the 3 hydrogens?
That's what I just said now, right? Next connecting atom only. We don't consider things as a group. We will see more examples and it will make a whole lot of sense. Yes?
Can you show the Z isomer one?
Yes. Oh, you want me to show you? Okay.
For this.
For this particular molecule? No problem. This would be the Z isomer, right? Because this is high priority, this is high priority, both of them are on the same side.
Same side meaning both on the top.
Yes. Right? This is priority 1, this is priority 1. They are on the same side of carbon-carbon double bond. Right? Okay? So this would be Z, that will be E. Right, in this case, you will get your answer more clearly. So this is the carbon-carbon double bond now. Now it's a real world example, so of course it's supposed to be a little bit tricky, right? So we have to decide the priority for every group which is present on carbon-carbon double bond. So on this carbon we have methyl, and here we have ethyl. So are we deciding on this basis? No, we are not. This is not a bulk theory where we are deciding on the basis of groups. As I said earlier, we have to decide on the next connecting atom, and we will have to continue going further and further unless we find the difference. So here the next connecting atom is carbon, the next connecting atom is carbon. But after carbon, it's a tie, right? How do we decide then which one takes higher priority? Then we go to the next atom. So after carbon, the next connecting atom is hydrogen here, but the next connecting atom here is another carbon. So on that basis, this part of the group takes high priority, that as a one group takes low priority. Does it make sense now? Right, so we have to look at the next connecting item. It will make more sense now. So the next atom is carbon. Here is also carbon. Now this is a cyclic compound, so it does not matter if you go from this way or that way. If we talk about the bulk itself, right? But since we don't talk about bulk here, so we go to the next connecting atom. So next connecting atom is oxygen here, and next connecting atom is carbon here. So out of oxygen and carbon, oxygen has higher atomic number. Therefore, this part takes high priority, and this part takes low priority. Does it clarify the question you were having before? That it's not about groups here. It is about the next connection. And we have to keep going further and further unless we find a difference. Alright? Any questions? This is new, I think, because I don't see any head nodding. So you haven't studied this before, right? Yeah, so this is more of a newer thing and very systematic, yes.
To be new carbon, no, it's connected to another carbon. So one carbon here, it's here only one carbon. Yeah. Each corner is a carbon.
That is the data.
And then hydrogens are equal.
Cis and trans, as I was telling you, fails terribly when we have all different groups.
Okay, fucked up.
So it has so many limitations. E and Z is super systematic. If we have all 4 different groups, then we cannot technically tell E apart from, cis apart from trans. Right? Any other question? I am withholding one information, which is, I'm just not giving it away yet. Yeah, I saw you. So I will come back to it later, or do you prefer it now? Now? You sure? I will only give it to you now if you say that, yeah, we understood everything until now. If there is some confusion remaining, then we will go later. Yes, 1 minute, please.
Sir, what happens if the double bond hole is directly opposite that? So how
What
do
are you saying? I don't understand. Yeah.
Like the double bond hole,
Double bond.
you move
Hole
it,
is
move it down.
here.
No, opposite, directly opposite.
Is there.
Yes, yes.
Then we will keep going, keep going, keep going, keep going, and if we can't tell, then we can't say that they are different. They will be same thing.
That will be the same.
Yeah.
So there's no
Yes, yes. Symmetrical molecule, right?
Yes.
So in symmetrical molecule, there will be no problem about isomers. Good question. Yes. That's what I'm talking about. If you look at things in a different perspective, you will always be giving yourself the answers to different questions. Yes.
Priority molecules will always be on the different atoms. Carbon concentration, it's not like bromide and magnesium were all the same carbon atom.
最后离子差不多。
So this was the example previously, right? You are saying that if this metal was there and this chlorine was there. That's what you are saying, right? No problem. Right? This is what you are saying. Right? No problem. Again, reassignment of priority, because this is a new molecule. So out of this and this, which one will take high priority?
Bromide?
Bromine, right? And out of this and this, which one will take high priority?
Chlorine.
Chlorine.
He doesn't put any on his neck.
So both are on the same side, hence this will be Z. No problem, right? Now we are talking.
So it looks
Yes,
extra.
ask me silly questions, stupid questions, so that we could develop
Every single
2 smart questions later.
detail you can see.
Not very often we will be able to ask $1 million question just out of the thin air. Right? A lot of work goes on to, brainstorming and so many things. Then you would be understanding that what could be the complications there. And I will admit to it if I don't know the answer. I mean, both of us can find it. But if you don't ask questions, you think that, well, it may sound silly. There are no silly questions. There are only silly answers. Right? Please. Right, so I feel that you are getting the hang of it now. If there is anyone who's asking to not give away the information which I am withholding right now, please raise your hand. It's not that important, I can give you that later as well, but yeah. If everyone is up to speed, then I can give it to you now as well, because later I may forget. So no one is not stopping me, right? See, I asked everyone and no one stopped me, so here you go. The thing which I withheld is that the double bond in CIP convention is counted twice. Right? So in this case, we have the carbon-oxygen double bond, right? So it would be as if that this carbon had two oxygens. Make sense? This is CIP convention. I'm just, translating it to you in English. Probably the same in English. So double bond is counted twice, triple bond is counted thrice. That's as per the CIP conventions. We will see more examples and it will be clarified in some cases where this will be effectively applied. But in this case, we didn't need this, right? But since it was there, so it reminded me that I withheld this information. Yes? Oh, I thought you were asking questions. Okay. That's all of E and Z and cis and trans for now. We have tutorial sessions for all these things, so we will do a lot of practice in there. Right, so the next topic I want you to note down here is some commercial uses of ethylene. Again, as I said, hundreds of uses. These are only my selection of what I find of importance. Acetic acid is a compound which is very, very much commercially available. It's used as a solvent in many things. It's used in your kitchen. You have eaten this molecule, probably you don't know it yet. That is vinegar. Yes, so vinegar is very low concentration of acetic acid. Ethanol, if you are up to the age, then probably you would have used it. If anyone underage, I'm so sorry. This is the dull talk. You can close your ear for a while. Yeah? Vinyl chloride or polyvinyl chloride, PVC, you might have heard. It's used in pipings and so many other plastic stuff. A lot of plastic could be made from alkene compounds, that's for sure. One of them is PVC or polyethylene. The soft plastic bags are basically made up of polyethylene. And then the hard plastic pipes and those things are actually made up of PVC. So these are examples of the most simple alkene, which is ethene. So the common name of ethene is ethylene. Yeah? Another example is propylene, which is technically propene. In IUPAC term, its name would be propene, but the common name is propylene. And then for me, these two are very good examples of their industrial or commercial use. The polypropylene is used in the luggage bags and all, right? I just bought a few luggage bags, so I am very familiar with these things. There are three types of luggage bags, technically speaking. One is made up of ABS, which is another polymer. Then it's polypropylene, and then it's polycarbonate. So to my research, polycarbonate is the most strongest one. I may be wrong. Time to find out when I travel somewhere. But yeah, polypropylene is also a common ingredient of the luggage bag plastic. And then acetone is very common solvents which is used in terms of different applications. A lot of reactions we can only perform in acetone. So again, very, very, very important and common application. Yeah. Right, so on this slide what I'm trying to show you, a bit complex, but if you would sets. So this is called enthalpy diagram, or you can simply call it energy diagram. We will be familiar with it in future few classes, but for now this is just an example. That in energy diagram, what we do is that we put the different steps of a reaction and we measure their energy expenditure or usage on y-axis. So you could see here that different types of alkenes having different terms of energy. This is higher on energy stage, this is lowest on this energy stage, if you look at only these three examples. And the difference between these three examples is what? The position of double bond or their orientation. So here we have one propene, here we have two propene, no, one butene, two butene in cis form and two butene in trans form. So you could tell from this diagram that the lowest energy is 2 propene in trans form, meaning that it will be more stable. This will be lesser stable and this will be the least stable. Right? So that is the whole purpose of this diagram. Why do I have these diagrams there? It will come later. First look at this. So the relative stabilities of alkene, all the possible cases I have given you here, that the more substituted the alkene is, the more stable it will be. And the least substituted it will be, the less stable it will be. Now everything is in between. Tetra substituted, because there are only 4 places where substitution could occur, would be the highest. Tri substituted would be then. Di substituted on one side of the carbon-carbon double bond will be higher in stability as opposed to on opposite side. On the opposite carbon, I mean. And within the opposite carbon, if they are on the opposite side, meaning trans, would be high stable. If they are cis, then would be less stable. So this is different than that, right? Can you see the difference? That here, the two substitutions are on the same carbon of the carbon-carbon double bond. But here, the two substitutions are on the different carbons. Then on different carbons, there are two possibilities, either cis or trans, right? Now, why trans and cis have difference? Because of course, the steric index. So when they are cis, they will have their electronic cloud mixed up with each other. There will be some electronic repulsion, and therefore, in terms of trans, we will not have that problem, and hence more stability. Right? So all 3 things are now clear. Any questions on this slide? Quite important, this slide, for your exam point of view. You may have some MCQs from this slide every now and then. I am not expecting that you should know the whole sequence, but if you know the sense of it, from the given example, you would be able to tell that which one will have high stability. And this all depends on, the steric index. And it does not always is true that tetrasubstituted will always be stable, because it depends on what groups are attached here. So I think I'm going in unnecessary detail now, because we will discuss that later. But yeah, it's not always true that tetrasubstituted will be most stable. It also depends on what are those groups. If groups are electron donating, yes. If they are withdrawing, no. No need to go in that detail for now, because that's definitely our topic for future. Any other question from this slide? All clear? Perfect. Let's talk about the chemical properties of alkenes then. So alkenes can be synthesized by elimination reaction. Now you know what is elimination reaction already, right? Because we looked at the examples for other cases. So in this cases, it's called dehydrohalogenation. Why? Because we are removing hydrogen and halogen from the given molecule. So hydrogen and halogen will be removed, and as a result you will have carbon-carbon double bond. Right? It is an example of elimination reaction, of course, right? But why are we giving it this name? Based on the suitability only. If you don't remember dehydrohalogenation, it's fine. As long as you can make from alkyl halide and alkene, good enough. Dehydrohalogenation is just the practical picture of the reaction. Now on the first part of this slide it says Saytzeff rule. So Saytzeff rule is something which could be tricky when you are making, it is written Saytzeff, but I am saying it's Saytzeff because Germany, again, so in German I think Z is S and S is Z. So this is actually Saytzeff. Whatever. This is not a German class anyway, right? So, what I was saying, yes, this rule becomes very useful when you are making alkenes by using elimination reaction. We will look at 2 examples, but what does this rule say? That in the elimination of HX from an alkyl halide, the more highly saturated alkene product predominates. So once you will see the mechanism of this reaction in next few slides, you could notice that there is possibility that you can make the double bond at one point or at another point. So then you will have to decide. How you will decide? You will remember the Saytzeff rule. Because Saytzeff rule says that when there is an opportunity of making 2 different carbon-carbon double bonds, you should make the one which is more substituted. Of course, this has something to do with the previous slide, because more substituted in most cases means more stable, right? So this is something to do with the stability. Once we will look at the structure, the mechanism, it will all make more sense. But for now, can you appreciate that Saytzeff guy here, probably dead by now, so I should call his name with some respect. So Sir Saytzeff is trying to help us in telling that which of the alkene we should form if we have multiple options. And that option is always should be more substituted. Yeah? Right, so this reaction can proceed with 2 different routes. One is called E2 mechanism and the other is called E1 mechanism. So E stands for elimination. Now these are the explanation of how the reaction goes through. E stands for what? Elimination. Now 2 actually indicates that 2 things are involved in this reaction. Right? Now how does E2 mechanism occurs is that the hydrogen and halogen is removed from the alkyl halide at the same time. And this happens when you use a strong base for this reaction. So base attacks on the hydrogen, it takes the hydrogen away from the molecule. So hydrogen goes in the form of proton by giving away its electrons to the carbon. We see that the movement of electron is towards carbon. These curly arrows actually indicates the movement of electrons. And the head is where the electrons are moving to. And tail is where they are moving from. So from hydrogen, they are moving towards carbon. While this is happening, this halogen is now an accessory to that intermediate, right? This is the intermediate I'm talking about. So you see that a new bond is being formed. And now this is excess bond. So this will be removed just by taking away the electrons by itself, because halogens are quite electronegative, right? So they can take away the electrons from this bond. And as a result, they will be eliminated in the form of halide, meaning halogen negative ion, right? And all this happens simultaneously. Simultaneously, as of that, this bond making and bond breaking, it does not require multiple steps. The attack of base to get the hydrogen and get rid of the halogen, it all occurs simultaneously. That's why we see these dotted lines. So dotted line means bond forming or breaking. So to indicate all this in one step, we call this type of a structure a transition state. Remember that in previous mechanism, when we were talking about free radical mechanism, I used the term intermediate. That free radical is an intermediate. So intermediate is a thing which is actually there and which you can, isolate from the reaction and study that. Transition state is a hypothetical thing. Here we are just showing that everything is happening simultaneously. And how we can show that on a piece of paper? By making these dotted bonds, which means that bond forming or bond breaking is happening at that point. Does it make sense? So this type of representation is called transition state. So in E2 mechanism, the reaction occurs simultaneously. E comes from elimination and 2 comes from that 2 things are important for this reaction. And those 2 things are your alkyl halide and your base. Alright? That's why the name of this mechanism is E2 mechanism. While after the bonds are formed and broken, then you get the alkene as you saw in the equation itself. Right? Any questions here? This might be a little bit advanced for some of you, but we will see more advanced mechanisms in next few chapters. So I want you to clarify all your doubts, if you have any, right now. So you can see, right, that this all could happen all at once. And by this representation, we are just showing that this bond making and breaking doesn't need to be done at a separate point of time. The moment base attacks on this molecule, halogen departs, hydrogen departs, and you get the carbon-carbon double bond. Right? Okay. Once you will compare it with the other type of mechanism, it will also make more sense. So if we have E2 mechanism, then of course there will be an E1 mechanism as well, right? So what was that reaction? Dehydrohalogenation, right? That from alkyl halide, by elimination reaction we made alkene. Another example by which we can make alkene is dehydration of alcohols. So this is again another example of elimination reaction. As the name suggests, dehydration would mean removal of water. Hydra, these kind of things are from water. And then D, if it's written from any reaction's name, it would mean the removal. So dehydration means removal of water. That's why I have written H and OH like that. So you can take away this part. If you take away this part, then you will get the carbon-carbon double bond. Right? Now this happens with a different mechanism. We will look at it later. But this is another example of elimination reaction by which you can synthesize alkenes. Right? Okay? Is it too much for today? What are you talking about? We still have like 15 minutes. And we started like 15 minutes late. I'm just kidding. Whatever you say. You want it to be over? Alright, I don't have a mic, so I can just drop my marker, right? Mic drop. So, over. Thank you so much.